The universe is impossibly vast and ancient, yet our understanding of it is being rewritten right now. We are about to embark on a journey through 25 of the most profound space discoveries that have completely shattered our old cosmic perspective. By the end of this, you will see the cosmos not as a static picture, but as a dynamic, living story. We will uncover why most of the universe is made of a ghostly substance we cannot see, and how a single strange signal from the 70s remains an enduring mystery. Which of these cosmic revelations do you think will change your view of reality? Our entire cosmic story began with a persistent, annoying hiss. In the year 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting their enormous horn antenna in New Jersey. They were plagued by a low, steady noise that came from every direction in the sky, a uniform static that just would not go away. They scrubbed the antenna clean, even evicting a pair of pigeons and their stubborn droppings, but the mysterious hum remained. This was no instrument error. They had accidentally stumbled upon the oldest light in the universe, the faint afterglow of creation itself. This cosmic microwave background radiation is the cooled remnant of the universe's fiery birth, the echo of the Big Bang. Its discovery was the final, irrefutable piece of evidence that our universe was not eternal and static, but had a definitive, explosive beginning. Think about that for a moment. Every galaxy, every star, every atom that makes up our world, our bodies, was once compressed into an unimaginably hot, dense point that began expanding some 13.8 billion years ago. That faint static, a whisper from the edge of time, completely rewrote our origin story, transforming cosmology from a search for a steady-state cosmos into the study of a dynamic, evolving universe. That faint echo of creation was not the only clue pointing toward a cosmic genesis. Decades earlier, another monumental discovery had already begun to pull the rug out from under a static, unchanging universe. Edwin Hubble, peering through the massive telescope at Mount Wilson, made an observation so profound it shattered humanity's comfortable, small view of the cosmos. He found that the universe is not standing still. It is running away from us. By meticulously measuring the light from distant galaxies, Hubble noticed something bizarre. The light from nearly every galaxy was shifted toward the red end of the spectrum. This redshift is similar to the Doppler effect you hear when a siren from an ambulance drops in pitch as it speeds away from you. The sound waves stretch out. For light, this stretching means the galaxy is racing away from our vantage point. The truly revolutionary part was what Hubble found when he compared this redshift to the estimated distances of these galaxies. The farther away a galaxy was, the faster it appeared to be receding. This direct relationship, now known as Hubble's law, painted a stunning picture. We are not living in a universe where galaxies are simply drifting through a vast, empty space. Instead, the very fabric of space itself is stretching, carrying the galaxies along with it, like raisins in an expanding loaf of raisin bread. As the dough rises, every raisin moves away from every other raisin. From any single raisin's perspective, all the others are fleeing, and the most distant ones appear to move the fastest. This single idea, the expanding universe, was the critical stepping stone that forced scientists to consider a radical beginning. If you could rewind this cosmic film, all that expanding space would contract, pulling all matter and energy back together, compressing it into that initial hot, dense state that we now call the Big Bang. Hubble's work did not just discover galaxies, it revealed the dynamic, breathing nature of the cosmos itself, a revelation that set the stage for everything that followed. Hubble's expanding universe revealed a cosmos in motion, but that motion soon presented a new and deeper puzzle. The real trouble began when astronomers tried to understand what was holding galaxies together. A Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies all bound by gravity. He measured how fast these individual galaxies were whipping around the cluster's center. The speeds he found were shockingly high. According to the laws of gravity and the amount of visible matter, like stars and gas, that he could see, the cluster simply did not have enough mass to hold onto these speeding galaxies. They should have flown apart, scattering into the void. Zwicky proposed that some form of invisible matter, which he called Dunkel Materie, or dark matter, must be providing the extra gravitational glue to keep the cluster intact. His idea was largely ignored for decades. Then, in the 1970s, astronomer Vera Rubin provided the definitive proof. She meticulously mapped the rotation of spiral galaxies, expecting to find that stars on the outer edges, far from the bright galactic center, would orbit more slowly, just as Pluto orbits the Sun more slowly than Mercury. But the data told a different, astonishing story. Stars on the fringes of galaxies were moving just as fast as those near the center. The entire galaxy was rotating so fast that it, too, should have torn itself apart. The only possible explanation was that each galaxy was embedded within a gigantic, massive halo of something invisible. This invisible substance, dark matter, does not emit, absorb, or reflect any light, making it completely undetectable to our telescopes. Its presence is only betrayed by its immense gravitational pull. We now know this ghostly stuff outweighs all the normal matter, all the stars and planets and gas clouds we can see, by a factor of 5 to 1. This means over 80% of the matter in the universe is made of a substance whose fundamental nature remains a complete mystery. We are living in a universe dominated by a cosmic phantom, an invisible architecture that holds the entire cosmic web together. So if dark matter provides the invisible anchor holding galaxies together, its gravitational pull should be putting the brakes on the cosmic expansion. For decades, astronomers assumed that the universe, while still growing, must be slowing down under the collective weight of all this matter. The big question was simply by how much. To find out, two independent teams set out in the late 1990s to measure the deceleration by observing incredibly distant stellar explosions known as Type 1, a supernova. These supernovae are cosmic mile markers, their known intrinsic brightness allowing scientists to calculate precise distances across billions of light years. By comparing these distances to the supernova's redshifts, which tell us how fast the universe was expanding when the star blew up, the teams could chart the expansion history of the cosmos. The results were not just surprising, they were mind-bending. The data revealed that the most distant and therefore ancient supernovae were fainter than expected. This could only mean one thing: they were farther away than anyone had predicted. The expansion of the universe was not slowing down at all, it was speeding up. Imagine gently tossing a ball into the air, expecting it to fall back to Earth, only to watch it shoot faster and faster into the sky, defying gravity itself. This is precisely what astronomers witnessed on a cosmic scale. Some mysterious, repulsive force was overpowering gravity, stretching the very fabric of space at an ever-increasing rate. This phenomenon was dubbed dark energy. We now believe this enigmatic force makes up about 68% of the entire universe. It is the dominant component of reality, and we have almost no idea what it is. The leading candidate is the energy inherent to empty space itself, a concept Einstein once proposed and then discarded as his greatest blunder. Dark energy presents the single greatest puzzle in all of physics, because its existence determines the ultimate fate of everything, a future where galaxies are torn apart, and the cosmos expands into an eternal, cold, and empty darkness. That shocking acceleration of the cosmos, driven by dark energy, forces us to ask a fundamental question: what were the initial conditions that set this entire cosmic story in motion? The answer lies etched into the oldest light we can see, the cosmic microwave background. When Penzias and Wilson first heard that faint hiss, it appeared perfectly smooth, the same temperature in every direction. But if the universe was truly that uniform at its birth, how did we get from that smooth beginning to the complex cosmic web of galaxies and voids we see today? The universe needed seeds, tiny imperfections where gravity could get a foothold. For decades, this was just a theory until a satellite called the Cosmic Background Explorer, or COBE, was launched. In 1992, the COBE team announced a monumental discovery. They had found minuscule variations in the temperature of the cosmic microwave background. These anisotropies, as they are called, are incredibly small, mere millionths of a degree. Yet these tiny ripples were everything. They were the gravitational seeds, the blueprints for the entire large-scale structure of the universe. Imagine a perfectly smooth sheet of rubber. Now imagine pressing your finger into it ever so slightly, creating a tiny, almost imperceptible dimple. That dimple represents a region where the density of matter was ever so slightly higher than the surrounding area. Over billions of years, gravity would relentlessly pull more and more matter into that dimple, amplifying it until it collapsed into a vast cluster of galaxies. The smooth regions, meanwhile, would become the great cosmic voids. Later missions, especially the Planck satellite, mapped these temperature fluctuations with breathtaking precision, creating a detailed baby picture of the universe when it was only 380,000 years old. This map is so exquisitely detailed that by reading its patterns, scientists can determine the universe's exact age, its composition of normal matter, and dark energy, and even its overall geometry, confirming that on the largest scales, our universe is flat. Every galaxy, every star, and every one of us exists because of those specific, frozen ripples in the first light. For centuries, that question of our place in the cosmos was purely philosophical. Were planets like Earth a cosmic fluke, or were they common? The answer arrived not with a triumphant announcement, but with a subtle, rhythmic wobble. In 1995, two Swiss astronomers, Michel Mayor and Didier Queloz, pointed their telescope at a star called 51 Pegasi, a star not so different from our own Sun. They were not looking for a planet directly, because a planet that far away is far too faint to see. Instead, they were looking for the star's telltale dance. They found it. The star was rhythmically moving toward us and then away from us, pulled by the gentle gravitational tug of an unseen companion. This wobble revealed a world completely unlike anything in our own solar system, a gas giant they named 51 Pegasi b. The astonishing part was its orbit. This massive planet, at least half the size of Jupiter, was not orbiting at a stately distance. It was whipping around its star in a blistering 4.2 days, so close that its surface would be scorching hot. This was a hot Jupiter, a type of planet our theories had never predicted. Its existence proved that other solar systems not only existed, but they could be wildly, strangely different from our own. The discovery shattered the lone example of our own solar system and flung the cosmic doors wide open. If one planet could be found so easily, how many more were out there? The hunt was on, and it would soon become a tidal wave of new worlds. The Kepler Space Telescope transformed that trickle of discovery into a flood. Launched in 2009, its mission was simple yet profound: to stare continuously at a single patch of sky containing over 100,000 stars, watching for the tiny, periodic dimming that occurs when a planet passes in front of its star. For years, Kepler watched, and the data it sent back was nothing short of revolutionary. It revealed that planets are not the exception, they are the rule. The average star in our galaxy has at least one planet orbiting it. Kepler found thousands of worlds, from scorched rocky spheres smaller than Mercury to puffy gas giants larger than Jupiter. It revealed an entire cosmic zoo of planetary architectures, with worlds orbiting binary stars, planets in wildly eccentric paths, and entire compact systems with multiple planets orbiting closer to their star than Mercury is to our Sun. But the most profound statistic to emerge from this census of worlds was this: based on Kepler's data. Scientists estimate there are likely billions of Earth-sized planets orbiting within the habitable zone of their stars, that Goldilocks region where temperatures are just right for liquid water to exist on the surface. This single realization has completely redefined our place in the universe. Our pale blue dot is not a singular sanctuary for life. It is one of countless potential gardens in a galaxy overflowing with real estate. The question is no longer if other Earths exist, but how many of them are living worlds right now as we speak. This cosmic abundance of worlds leads us to another profound mystery, one born from the mind of Albert Einstein. His theory of general relativity predicted that massive objects warp the fabric of space and time, but it also hinted at the most extreme consequence of this warping, a place where gravity becomes so powerful that it traps everything, even light itself. For decades, these objects, which we now call black holes, were considered little more than a mathematical curiosity, a theoretical possibility that might not actually exist in nature. The first real evidence came not from seeing a black hole, but from hearing the universe. In 1971, astronomers detected powerful, regular X-ray pulses coming from a star system called Cygnus X1. The data revealed that a massive, invisible object was pulling gas from a companion star. As this gas spiraled inward, it heated to millions of degrees, screaming in X-rays just before it vanished forever beyond an invisible boundary, the event horizon. This was the first compelling proof that black holes were real. But the true confirmation of their role as cosmic architects came from studying the hearts of galaxies. We now know that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center, with a mass millions or even billions of times that of our Sun. These gravitational monsters are not just passive vacuum cleaners. They are active, dynamic forces that shape the evolution of their entire galaxies. When a black hole feeds, the infalling matter can release unimaginable energy, powering brilliant beacons known as quasars and driving colossal winds that can heat surrounding gas and halt star formation across the galaxy. The black hole, in essence, acts as a cosmic regulator. The ultimate proof arrived in April 2019, when the Event Horizon Telescope collaboration unveiled an image that stunned the world. It was not a picture of a black hole itself, for that is impossible, but of its shadow, a dark silhouette cast against the glowing, superheated matter swirling around it. This fiery ring, the photon sphere, marked the point of no return, the event horizon of the supermassive black hole at the heart of the galaxy Messier 87. To capture this image, scientists synchronized a global network of radio telescopes, effectively creating an Earth-sized observatory capable of resolving an object the size of a donut on the Moon. This monumental achievement transformed black holes from abstract mathematical concepts into observable, physical realities. They are the universe's ultimate paradoxes, simple in their essence yet holding secrets about the fundamental nature of space, time, and gravity that we are only beginning to unravel. Einstein's cosmic fabric does not just bend, it ripples. For a century, his theory of general relativity predicted that cataclysmic events should send waves traveling through the very substance of spacetime itself. Yet these gravitational waves were so incredibly faint that Einstein himself doubted we would ever detect them. They were a ghostly whisper lost in the cosmic noise. That all changed on the morning of September 14, 2015. At the Twin Laser Interferometer Gravitational Wave Observatory detectors, one in Louisiana and the other in Washington State, a signal arrived. It was not a sound you could hear, but a vibration recorded as a squiggle on a graph, a wobble in the laser beams that run through the detector's 4-kilometer-long arms. For a fleeting 20 milliseconds, the fabric of space around Earth stretched and squeezed by a distance smaller than the width of a proton. This tiny tremor was the death cry of two massive black holes, one with the mass of 29 suns, the other 36 times the mass of our Sun, locked in a final, fatal dance over 1 billion light-years away. They spiraled around each other, closer and faster, until they finally merged into a single, more massive black hole. In that last violent instant, a portion of their combined mass, equivalent to 3 whole suns, was converted directly into pure energy, shaking the universe and sending these gravitational waves racing outward at the speed of light. This was not an observation of light or X-rays or radio waves. This was a completely new sense, allowing us to feel the vibrations of the cosmos directly. It confirmed a cornerstone of Einstein's theory and inaugurated an entirely new field of astronomy. We are no longer just stargazers. We are now universe listeners, tuning into the deepest, most powerful symphonies of the cosmos, events that are completely dark and silent to every traditional telescope ever built. Listening to the cosmos shake with gravitational waves reveals the universe's most violent events, but it does not explain a far more fundamental mystery. Why does anything in the universe have substance at all? Why do the fundamental particles that build atoms, and by extension you and me, have any mass to begin with? For decades, the answer was a ghostly prediction, a missing piece in our most successful theory of particle physics. The Standard Model is a magnificent framework that describes all the known fundamental particles and 3 of the 4 forces of nature. Yet for it to work, the universe needed a kind of invisible energy field stretching through all of space. Think of this field as a cosmic vat of molasses. As particles move through it, they interact with this sticky field, and that interaction is what we experience as mass. Some particles, like photons, which are particles of light, zip through without any interaction at all, which is why they are massless and travel at the speed of light. Others, like electrons and quarks, get bogged down, acquiring their mass. The theoretical particle associated with this field, the proof of its existence, was named the Higgs boson. Finding it became the single most important quest in all of physics. The hunt required the most complex machine ever built, the Large Hadron Collider. Buried deep underground in a 17-mile circular tunnel beneath the border of Switzerland and France, this colossal instrument smashes protons together at velocities incredibly close to the speed of light. These collisions recreate, for a fleeting fraction of a second, the searing conditions that existed just after the Big Bang. For years, thousands of scientists sifted through the debris of countless collisions, looking for a specific, telltale signature. Then, on July 4, 2012, the announcement came: they had found it. The Higgs boson was real. This was not just the discovery of another particle. It was the discovery of the mechanism that gives the universe its substance. It completed the Standard Model, confirming a 50-year-old theory and answering one of the most basic questions we can ask. Why is the universe not just a soup of massless particles flying around at the speed of light? Because of the Higgs field, particles could coalesce, form atoms, then stars and planets, and eventually us. It is the reason matter has the property to clump and build. Without it, the cosmos as we know it would simply not exist. That same year, another cosmic signal was detected, one so precise and regular it was almost mistaken for a message from an alien civilization. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a radio telescope she had helped build. She noticed a tiny, repeating signal, a pulse so exact it ticked every 1.337 seconds. It was unlike anything seen before, a perfect celestial metronome emerging from the depths of space. The signal was so unnervingly regular that her team half-jokingly labeled it LGM-1, for Little Green Men. But soon, more of these pulsing objects were found across the sky. They were not alien beacons. They were something just as wondrous, the spinning corpses of massive stars. When a giant star dies in a supernova, its core can collapse into an unimaginably dense ball of neutrons, a city-sized object with more mass than our Sun. This neutron star spins incredibly fast, and its intense magnetic field focuses beams of radiation from its magnetic poles. Like a cosmic lighthouse, these beams sweep through space, and each time one crosses our line of sight, we see a pulse. These pulsars are the universe's most precise clocks. Their rhythmic flash is so reliable that the timing is more accurate than any atomic clock we can build on Earth. This incredible precision has made them indispensable tools for testing the very fabric of reality. By carefully tracking the pulses from a pair of pulsars orbiting each other, astronomers have provided the most stringent tests yet for Einstein's theory of general relativity, observing how their orbits decay as they radiate energy away in the form of gravitational waves. But perhaps their most surprising role was in the hunt for other worlds. In 1992, astronomers monitoring a pulsar named PSRB 1257+12 noticed minuscule, periodic variations in its clockwork pulses. The timing was ever so slightly off, as if the pulsar were wobbling in space. The cause was the gravitational tug of planets orbiting it. This was the very first confirmed discovery of planets outside our solar system, a system of alien worlds orbiting a stellar corpse, a full 3 years before the first exoplanet around a sun-like star was found. From a signal mistaken for aliens to the precise confirmation of Einstein's theories and the first glimpse of distant planets, pulsars have proven to be one of the cosmos's most versatile and surprising gifts. That rhythmic ticking from a dead star was a cosmic wonder, but it paled in comparison to the brilliant beacons that began to appear on the celestial maps of the 1960s. Radio astronomers were pinpointing objects that looked like faint stars, but they were pouring out a torrent of radio waves. When they examined the light from these so-called quasi-stellar radio sources, or quasars, they got the shock of their lives. The light was dramatically shifted to the red, meaning these objects were not just distant. They were at the very edge of the observable universe. This presented a staggering paradox. To appear as bright as they did from such mind-boggling distances, each quasar had to outshine an entire galaxy of hundreds of billions of stars. Yet they were doing this from a region of space smaller than our own solar system. What kind of cosmic engine could possibly be that small and that ferociously powerful? The only conceivable answer was a supermassive black hole, a monster weighing in at millions or even billions of times the mass of our Sun. But a black hole by itself is dark. The brilliance comes from the black hole's last meal before the long cosmic fast. As vast clouds of gas, dust, and even entire stars fall toward the event horizon, they don't go quietly. They form a swirling, superheated disk of material called an accretion disk, spinning at nearly the speed of light. Friction within this disk heats it to temperatures of millions of degrees, causing it to glow with the intensity of 1 trillion suns. Before the material vanishes forever, a portion of it gets funneled by the black hole's immense magnetic fields into 2 powerful jets that shoot out from its poles at nearly the speed of light, beaming radiation across the cosmos. We are seeing the violent, messy process of a black hole feeding, a brief and glorious phase in a galaxy's life. The sheer number of quasars in the distant universe tells us something profound about cosmic history. The universe was a far more violent and energetic place in its youth, with galaxies frequently merging, stirring up gas, and sending a bounty of fuel toward their central black holes. As the universe aged and the gas was consumed or blown away, these brilliant quasars mostly faded, leaving behind the quieter, dormant supermassive black holes we find at the hearts of galaxies today, including our own Milky Way. Quasars are not just distant curiosities. They are the cosmic lighthouses that first illuminated the existence of these gravitational giants, proving that the darkest objects in the universe can, for a time, become the brightest. These brilliant quasars illuminate the most distant reaches, but something far closer and more subtle is tugging at our entire galactic neighborhood. For decades, astronomers have noticed a strange and persistent drift in the motion of our galaxy and its neighbors. The entire local group of galaxies, including the Milky Way and Andromeda, is not moving randomly. It is being pulled as if by a cosmic river toward a specific point in the sky, deep in the direction of the constellation Centaurus. This mysterious gravitational focal point was named the Great Attractor. The sheer scale of this pull is staggering. Our galaxy is rushing toward it at a breathtaking speed of over 600 kilometers per second. But what could possibly possess enough gravitational might to command the motion of thousands of galaxies? The initial problem was that the proposed location of the Great Attractor lay in what astronomers call the zone of avoidance, a region of the sky obscured by the thick dust and dense starlight of the Milky Way's own galactic plane. It was like trying to see a distant mountain range through a dense, blinding fog. For a long time, the true nature of this cosmic magnet remained hidden. The breakthrough came with new tools that could see through the cosmic fog. Instruments using radio waves and infrared light, which can penetrate dust, began to map the hidden structures behind our galaxy's bulge. What they revealed was not a single, monstrous object, but something far more profound. The Great Attractor is not a lone giant. It is the heart of a colossal supercluster of galaxies, an immense knot in the cosmic web known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is an appropriate name for a structure that spans 500 million light-years and contains over 100,000 galaxies, all flowing along invisible rivers of gravity toward a common center. Our Milky Way is not being pulled by a single point, but is instead riding a vast gravitational watershed, a continental slope on a cosmic scale. The true source of this immense pull is not just the visible galaxies we can now map. The primary engine is the unimaginable amount of dark matter that clumps in these regions, forming a gravitational potential so deep that it dictates the motion of everything for hundreds of millions of light-years around it. The Great Attractor is the ultimate proof that the universe is not uniform. It is a tapestry of flows and currents, where dark matter sculpts the paths of the luminous galaxies we can see, guiding them on a journey we are only just beginning to map. Far beyond the last known planets, in the deep freeze of our solar system's outskirts, lies a realm of ancient ice. For centuries, comets seem to appear from nowhere, visiting the inner solar system on long, looping orbits before disappearing again into the darkness. Where did they come from? The answer began to take shape with a Dutch astronomer named Jan Uwit. He proposed that the Sun's gravitational influence did not simply stop at Pluto. Instead, it held sway over a vast, spherical shell of icy objects so distant that it could take them thousands, even millions of years to complete a single orbit. This theoretical reservoir, now called the Uwit Cloud, is thought to be the source of those long-period comets that swing into our view on rare occasions. But there was another, closer source. In the 1990s, astronomers began finding small, icy worlds orbiting the Sun just beyond Neptune. This region, known as the Kuiper Belt, is a sprawling, donut-shaped ring of frozen leftovers from the solar system's formation. The discovery of its first large object, a body named Albion, confirmed its existence. Then came a world that would change everything, a Kuiper Belt object larger than Pluto. Its discovery in 2005 forced astronomers to confront a simple question. If Pluto is a planet, then so is this new world, Eris, and likely dozens more. This led directly to Pluto's reclassification as a dwarf planet, a decision that reshaped our mental model of the solar system from a tidy set of 9 planets to a much more dynamic and crowded arrangement. The Kuiper Belt and the even more distant Uwit Cloud are not empty wastelands. They are the solar system's deep freezer, preserving the original building blocks of planets in pristine condition for billions of years. Every comet that visits us is a piece of this frozen archive, a time capsule carrying the same unaltered ice and organic compounds that were present when the Sun was young. These distant reservoirs are the final, missing pieces of our solar system's architecture, revealing a boundary that is not a sharp edge, but a gradual fading of the Sun's dominion into the vast population of interstellar space. The same water that carved our ancient riverbeds once flowed on the world next door. For centuries, Mars appeared in our telescopes as a dry, rusty sphere, a seemingly dead world. That perception began to crumble with the very first orbital missions. The Mariner and Viking orbiters in the 1960s and 70s sent back images that were tantalizingly familiar, showing vast canyons, meandering channels, and features that looked exactly like dry riverbeds. The evidence was circumstantial, but it was powerful. Mars had the ghost of a water cycle etched into its face. The true revolution, however, came from the rovers. When the little Sojourner rover of the Pathfinder mission bounced onto the surface in 1997, it was the first in a line of robotic geologists that would read the planet's story stone by stone. The twin rovers Spirit and Opportunity, landing in 2004, provided the smoking gun. Opportunity, in particular, found itself in a place called Meridiani Planum, and almost immediately it rolled right up to bedrock that was layered with cross-bedding, a pattern formed by flowing water. It then used its abrasion tool to grind into a rock and found spheres of the mineral hematite, nicknamed blueberries, which on Earth form in saturated, watery environments. The rover's ultimate discovery was a specific type of clay mineral that only forms in the presence of neutral, non-acidic water, the kind of water that could have supported life. The narrative shifted from a world that might have had brief, catastrophic floods to one that enjoyed a long, quiet, and wet history. But the story of Martian water did not end in the ancient past. Orbiters like Mars Reconnaissance Orbiter began spotting something bizarre and dynamic: dark, narrow streaks that appeared on sun-facing slopes during the warmer months, and then faded in the winter. These recurring slope lineae were the best evidence yet for liquid water on Mars today. The leading theory suggested that salts in the Martian soil could absorb water vapor from the thin atmosphere, creating a super salty brine that could remain liquid for a short time, just enough to trickle down a hillside. This transformed Mars from a museum of past habitability into a world that might still have active, albeit subtle, hydrological processes. The most recent chapter is being written by the Curiosity rover, which has been exploring an ancient lakebed inside Gale Crater for years. It has drilled into rock that was literally mud at the bottom of a standing lake that existed for millions of years. The Perseverance rover is now collecting samples from a fossilized river delta, a place where water once deposited sediments and, crucially, concentrated any potential signs of ancient life. The entire search for life on Mars is now guided by the certainty that it was once a world of rivers, lakes, and possibly even a northern ocean. The red planet is no longer a symbol of desolation, but a cold, dry desert holding the secrets of a warmer, wetter, and potentially living past. If life ever did spark there, we now know it had every ingredient and opportunity to do so. That wet, ancient Mars forces us to ask a profound question about time itself. How old is the stage upon which these cosmic dramas have played out? For most of human history, the age of the universe was a matter of pure speculation, with estimates ranging from a few thousand to an infinitely old cosmos. The answer required two precise and independent cosmic clocks, one that ticks with the expansion of space, and another frozen in the first light of creation. The Hubble Space Telescope dedicated years to refining the first clock, the expansion rate of the universe known as the Hubble constant. By observing pulsing stars called Cepheid variables in nearby galaxies and correlating them with distant supernova, Hubble's data gave us our most accurate measurement of how fast the cosmos is growing. This rate, the Hubble constant, is like a cosmic speedometer. If you know how fast the universe is expanding now, you can theoretically rewind the film all the way back to the beginning, to the moment of the Big Bang. That calculation gives you one estimate for the universe's age. But to trust that number, we needed a second, completely different clock to confirm it. That second clock was provided by the Planck satellite, which studied the cosmic microwave background in exquisite detail. The tiny temperature fluctuations in this ancient light are a frozen snapshot of the infant universe, and their specific pattern encodes a wealth of information about the universe's composition and expansion history. By analyzing these ripples, Planck could independently calculate the Hubble constant and thus the universe's age. The stunning result, when combined with the Hubble data, was a single definitive number. The universe is 13.8 billion years old. This is not a rough guess. It is one of the most precisely known numbers in all of science, confirmed by two entirely different methods looking at opposite ends of time. This timeline gives us a reliable framework for cosmic history. We now know that for the first 380,000 years, the universe was a hot, opaque plasma. Then, as it cooled, atoms formed and the first light could travel freely, creating the cosmic microwave background we see today. Galaxies began to assemble a few 100 million years later, and our own solar system is a relative newcomer, forming just 4.6 billion years ago. Every star you see, every galaxy in the deep field images, fits within this grand and precisely measured chronology, a story 13.8 billion years in the telling. That cosmic timeline reveals a universe in constant motion, a truth that applies not just to the expansion of space, but to the very galaxies themselves. We once pictured them as majestic, finished islands, floating in serene isolation, but the reality is far more savage and dynamic. Our own Milky Way, a graceful spiral of hundreds of billions of stars, has a hidden history written in the faint, ghostly rivers of light that swirl around it. These are stellar streams, the shredded remains of smaller galaxies that ventured too close and were torn apart by our galaxy's immense gravity. They are the evidence of galactic cannibalism, a process where large galaxies grow by consuming their smaller neighbors. The most famous of these is the Sagittarius dwarf spheroidal galaxy, a tiny satellite that has been orbiting the Milky Way for billions of years. With each pass, our galaxy's tidal forces pull it apart, stretching its stars into a long, faint ribbon that wraps around the entire galactic core. But this is not just a story of the past. Right now, the Milky Way is in the process of digesting another victim, a small galaxy whose remnants are known as the Gaia sausage, named for the distinctive sausage-shaped orbit its stars follow, and the European Space Agency's Gaia mission that discovered them. This violent merger, which occurred 8 to 10 billion years ago, may have delivered a huge influx of stars and gas that fundamentally reshaped our galaxy, perhaps even giving birth to its thick central bulge. When you look at the serene band of the Milky Way arching across the night sky, you are not looking at a static collection of stars. You are witnessing a cosmic predator, a dynamic system that is still growing, still evolving, and still feeding on the smaller galaxies that share its cosmic neighborhood. This process of galactic cannibalism is the dominant way that large galaxies like our own have built themselves up over billions of years. It shows us that the universe is not a peaceful gallery of finished works. It is a construction site where the grandest structures are assembled through a long and violent history of collisions and mergers. Our galaxy's predatory nature reveals a cosmos of constant interaction, but our solar system has its own protective shield, a fragile bubble in the galactic river. For decades, its true shape and extent were pure speculation, until two small, intrepid spacecraft gave us the ultimate frontier crossing. Voyager 1 and Voyager 2, launched in 1977, were designed to explore the outer planets, but their greatest mission began long after those encounters were over. They kept flying, racing toward the edge of the sun's influence. This boundary is not an empty void. The sun constantly exhales a stream of charged particles, the solar wind, which blows outward in all directions. This wind carves out a vast cavity in the local interstellar medium, the thin gas and dust that fills the galaxy. This protective envelope is our heliosphere, a magnetic bubble that shields every planet in our solar system from the harsh, high-energy cosmic rays that flood interstellar space. The question was, where does this bubble end? The answer came in stages. First, Voyager 1 encountered the termination shock, a region where the solar wind, having traveled for billions of miles, suddenly slows down from supersonic to subsonic speeds as it begins to press against the interstellar wind. But the final frontier was the heliopause. This is the true boundary, the surface where the outward pressure of the solar wind finally balances the inward pressure of the galactic environment. In August 2012, Voyager 1's instruments registered a dramatic drop in particles from the Sun and a corresponding surge in cosmic rays from outside. It had pierced the heliopause and become the first human-made object to enter interstellar space. The data revealed a startlingly complex and dynamic interaction. Imagine our solar system sailing through the galaxy like a ship, its heliosphere forming a protective bow wave and a long, trailing tail, much like a comet. The shape of this bubble is not static. It breathes and shifts with the Sun's 11-year activity cycle, when solar storms send stronger winds that momentarily push the boundary farther out. Voyager 2's later crossing at a different point in the heliosphere confirmed this complexity, showing that the magnetic field of local interstellar space folds back over the bubble, creating a layered and porous frontier. These two tiny probes, now billions of miles from home with fading power, have fundamentally changed our understanding of our local cosmic address. We do not simply orbit a star in empty space. We are nestled inside a dynamic, protective magnetic cocoon, one that is constantly being shaped and reshaped by its journey through the galaxy. That protective bubble we call home exists within a universe of astonishingly uniform properties. But this cosmic consistency presented a deep puzzle for decades. If the universe began in a chaotic fireball, how did it become so smooth and flat on the largest scales? Regions of space now billions of light-years apart were once close enough to interact, yet they have the exact same temperature and density, as if they had somehow reached a perfect equilibrium. This is like walking into a vast, crowded room and finding that every single person, without having spoken, has decided to wear the exact same outfit. How could this have happened? The most elegant solution is a theory called cosmic inflation. This idea proposes that in the very first fraction of a second, a minuscule sliver of time around 10 to the power of -36 seconds after the Big Bang, the universe underwent a breathtaking growth spurt. Space did not just expand, it inflated exponentially, doubling in size repeatedly in an unimaginably short burst. In less than a blink of an eye, a subatomic speck of the primordial universe was stretched to a size larger than our entire observable cosmos today. This violent, faster-than-light expansion solved the uniformity problem instantly. It took a tiny, homogeneous patch of the early universe and stretched it into the vast, smooth canvas we now observe. Everything we see was once crammed into a region small enough to have been in causal contact, to have mixed and settled into a uniform temperature before inflation blew it up to cosmic proportions. But inflation did more than just iron out the wrinkles. It also created them. According to quantum theory, empty space is not truly empty. It is a seething foam of virtual particles constantly flickering in and out of existence. During the inflationary period, these microscopic quantum fluctuations were stretched to astronomical sizes. The tiny density variations, the random hills and valleys in the fabric of spacetime, became the seeds for all future structure. They were the primordial blueprints, the slight overdensities where dark matter could begin to clump, eventually pulling in normal matter to form the first stars, galaxies, and the vast cosmic web. The evidence for this incredible event is written in the cosmic microwave background. The Planck satellite's exquisitely detailed map of the CMB's temperature variations shows a pattern that matches the predictions of inflation perfectly. The sizes of the hot and cold spots, their distribution across the sky, it all points to a universe that underwent this rapid, exponential expansion. Without inflation, the universe would be a much lumpier, more chaotic place. We owe the very existence of galaxies, and by extension ourselves, to those quantum tremors, magnified by inflation into the gravitational foundations of the cosmos. It was the universe's first and most dramatic act, setting the stage for everything that was to follow. Our universe appears to be perfectly fine-tuned for life, a cosmic coincidence so precise it defies easy explanation. Why do the fundamental forces have just the right strength to allow atoms and complex molecules to form? Why is the amount of dark energy so delicately balanced that it permits galaxies to assemble instead of tearing space apart? The multiverse hypothesis offers a radical answer to this riddle of fine-tuning. It suggests that our universe may not be a single, lonely entity, but merely one bubble in a vast, bubbling cosmic foam. This is not science fiction, but a serious proposal emerging from the frontiers of cosmology and physics. The theory of cosmic inflation, which explains the uniformity of our universe, may be an eternal process. In this eternal inflation, pockets of space can stop inflating and settle into stable universes, while the space between them continues to expand exponentially forever. Each of these pocket universes could have randomly selected different physical constants and laws during its formation. In most of them, the constants would be wrong for life. Stars might not ignite, or atoms might never form. We find ourselves in a universe that works not because it was designed, but because it is one of the rare, habitable ones in an unimaginably vast ensemble where every possibility is realized. This idea finds another anchor in string theory, a candidate for a theory of everything. String theory suggests that the fundamental particles are tiny, vibrating strings, and the way they vibrate determines the laws of physics. But the mathematics of string theory points not to one unique set of laws, but to a colossal landscape of possibilities, perhaps 10 to the power of 500 different vacuum states, each representing a universe with its own distinct physics. The multiverse concept shatters the traditional scientific expectation that the laws of nature are universal and immutable. It implies that our laws are merely local bylaws, applicable only within our cosmic bubble. What we call reality is just a single page in an infinite cosmic library. This is perhaps the most profound and humbling shift in perspective yet. It challenges the very premise of our search for a single, elegant theory of everything. Are we discovering the fundamental rules of existence, or are we merely cataloging the parochial customs of our own tiny cosmic neighborhood? The multiverse stretches the definition of reality to its breaking point, forcing us to confront the possibility that everything we know is just one version of an infinite number of cosmic stories. That cosmic library of infinite possibilities holds many strange and sudden pages, one of which delivers its message in a blast of pure power lasting less than the blink of an eye. In 2007, astronomers were sifting through old data from the Parkes Radio Telescope in Australia, searching for new pulsars. What they found instead was a single, blistering spike of energy that had arrived from deep space years earlier. It was a flash of radio waves so intense it saturated the detectors, yet it lasted for only 5 milliseconds. This was the first recognized fast radio burst, or FRB, a cosmic scream that arrived without warning and then vanished. For years, it was a solitary mystery, and many wondered if it was just a one-off glitch. But then more were found. These bursts are now detected regularly, some from random locations, others repeating from the same spot in the sky. Their extreme brevity and incredible power are the core of the puzzle. In a few thousandths of a second, an FRB can release more energy than our sun puts out over several days. To do that from across billions of light years requires an engine of almost unimaginable ferocity. The leading suspects are magnetars, which are neutron stars with magnetic fields so powerful they could strip the information from a credit card from halfway across the solar system. A starquake on such a magnetar could snap its magnetic field lines, releasing a titanic shockwave that blasts out a radio burst. Other theories involve cataclysmic collisions or material falling onto a black hole, but the repeating bursts rule out any one-time destructive event for many of them. Yet the true genius of these signals is not just in their source, but in their journey. As an FRB travels across millions or billions of light years, it passes through the diffuse clouds of gas and dust that make up the cosmic web. This material, mostly lonely protons and electrons, is so hot and spread out that it is completely invisible to our telescopes, but it does something to the radio burst. It slows it down. The different radio frequencies within the burst travel at slightly different speeds, with the higher frequencies arriving at our telescopes a fraction of a second before the lower ones. This delay, called dispersion, is like a cosmic barcode. By measuring how much the burst has been stretched, astronomers can count the total number of electrons it has encountered on its long journey, effectively weighing all the normal matter in its path. For decades, cosmologists had a problem. When they added up all the normal matter they could see in stars and galaxies, it only accounted for about half of the amount that should have been created in the Big Bang. The rest was missing, presumed to be hiding in these vast, invisible filaments of hot gas in the voids between galaxies. Fast radio bursts are now acting as cosmic scales, probing these dark corridors. The dispersion from just a single burst can reveal the total amount of matter in a line stretching all the way back to the dawn of time. The measurements confirm it. The missing matter is indeed there, woven through the empty spaces. These brilliant, mysterious flashes are therefore more than just a cosmic curiosity. They are both a message from some of the most violent objects in existence and a precise tool, allowing us to finally see the invisible threads of the cosmic web itself. Those brilliant, fleeting flashes of radio energy are cosmic messengers from the farthest reaches, but their journeys are set against the backdrop of an even grander narrative, the ultimate fate of everything. For centuries, humanity envisioned a cyclical universe, one of eternal return, or a steady-state cosmos that simply persisted forever. Today, our discoveries have painted a far more definitive and chilling portrait of the end. The destiny of the cosmos is a battle between two titans, the relentless pull of gravity and the repulsive push of dark energy. And every measurement we have tells us that dark energy is winning decisively. This leads us to several possible endings, all of them lonely. The most accepted scenario is known as the heat death, or the big freeze. In this future, the universe continues to expand and accelerate forever. Galaxies will be pulled so far apart that the light from one will never reach another. Within each galaxy, stars will gradually burn through their fuel. The last stars, small red dwarfs, will eventually flicker out after trillions of years, leaving behind cold, dead remnants, black holes, neutron stars, and frozen planets. Over near-infinite timescales, even black holes are not permanent. They slowly evaporate through a quantum process known as Hawking radiation, vanishing in a final puff of particles. The universe would then become a vast, dark, and near-perfect vacuum, a cosmic graveyard where the temperature approaches absolute zero and no complex process, no life, no light, can ever exist again. It is a quiet, cold, and gradual end. But what if dark energy is even more strange and potent than we think? A more violent alternative is the Big Rip. This scenario depends on the strength of dark energy's repulsive force. If it increases over time, becoming stronger and stronger, it would not just push galaxies apart. First, it would tear apart galaxy clusters, then individual galaxies. As the end draws near, the expansion force would overcome the gravity holding stars within a galaxy, flinging them into the void. Then it would rip apart solar systems. In the final moments, the fabric of space-time would tear itself apart at every scale. The force would overcome the electromagnetic bonds holding planets together, shredding them. It would overcome the nuclear forces holding atoms together, tearing every nucleus and every particle apart from every other. the universe would end not in cold silence, but in a catastrophic, instantaneous disintegration of spacetime itself. While the data currently favors the long, cold freeze of the heat death, the Big Rip remains a haunting possibility. These are not just abstract doomsday scenarios. They are the direct, logical conclusions drawn from our measurements of dark energy and the geometry of the universe. The fact that we can even contemplate such endings is a testament to how far our cosmic understanding has come. We have moved from a small, eternal cosmos to a vast, dynamic, and finite one with a clear, and ultimately solitary, destiny. The story of the universe, it seems, has a final, irreversible chapter. The universe's final, cold fate seems to stand in stark contrast to the vibrant phenomenon of life. Yet the chemical seeds for biology are sown everywhere, even in the darkest voids between the stars. For a long time, we assumed that the empty space between star systems was a sterile vacuum, far too harsh and cold for the delicate chemistry of life to ever begin. We were wrong. Radio telescopes, tuned to listen to the faint whispers of molecules, began picking up the signatures of complex organic compounds in vast, cold clouds of gas and dust. These were not just simple atoms. Astronomers found molecules like formaldehyde, ethanol, and even sugars and amino acids, the very building blocks of proteins. How could such complexity arise in the freezing darkness of an interstellar cloud? These clouds are cosmic chemistry labs. Dust grains act as miniature platforms, where atoms and simple molecules stick to their frigid surfaces. Over millions of years, they slowly jostle and react, building up into more complex structures, aided by the raw energy of starlight. When a new star system begins to form from one of these clouds, all these pre-made organic ingredients are incorporated right into the mix. We have now seen these molecules in the swirling protoplanetary disks around young stars, the very places where planets are being born. This means that from the very beginning, the recipe for life is written into the raw materials of new worlds. The final proof that this celestial ingredient delivery system works came from missions to asteroids and comets. Spacecraft like Rosetta, which rendezvoused with a comet, analyzed its composition directly and found a rich soup of organic molecules, including the amino acid glycine. Meteorites that have fallen to Earth, chunks of asteroids, have been found to contain a wide array of these compounds. This tells a stunning story. The universe is not chemically barren. It is preloaded with the fundamental building blocks of biology. The transition from non-living chemistry to living biology still remains a profound mystery, but we now know that the first and most crucial step, the creation of the necessary organic ingredients, is a universal process. It happens in the dark molecular clouds, it happens in the planetary nurseries, and it is delivered to the surfaces of young planets by comets and asteroids. The emergence of life on Earth was not a chemical miracle that happened in isolation. It was the result of a galaxy that is already, and everywhere, pregnant with the potential for life. A silent ripple in space-time and a brilliant cosmic flash arrived at nearly the same instant, delivering a message that would solve a mystery as old as human greed. On August 17, 2017, the LIGO and Virgo gravitational wave detectors felt the distinctive chirp of two massive objects spiraling together. This was not the deep thud of black holes which vanish without a trace. This signal was different, lighter, and it lasted longer. Just 2 seconds after the gravitational wave alert, orbiting telescopes caught a burst of gamma rays from the same patch of sky. For the first time ever, we had both felt the shudder and seen the fire. The source was a galaxy called NGC 4993, 130 million light-years away. Telescopes around the world and in space swiveled to watch. What they witnessed was a kilonova, an explosion 1,000 times brighter than a typical nova. As two ultra-dense neutron stars circled each other hundreds of times per second, They ripped each other apart in a final, violent embrace. The collision forged a cosmic crucible, creating conditions more extreme than any supernova. In that fleeting, radiant fireball, a phenomenal alchemy took place. Scientists had long theorized that the universe's heaviest elements, like gold, platinum, and uranium, could not be forged in the heart of a star or even in a standard stellar explosion. The process required a rapid capture of neutrons, a frantic assembly line that could only occur in an environment flooded with free neutrons. A neutron-star merger is exactly that, a place where the very building blocks of atomic nuclei are squeezed out into space. The observed light from the kilonova carried the specific chemical fingerprints of these heavy elements being synthesized in real time. The calculations were staggering. That single event likely produced an amount of gold equal to several hundred times the mass of our entire planet, along with vast quantities of other precious metals, all scattered into the cosmos to one day become part of new stars, planets, and perhaps even life. Every piece of gold jewelry on Earth, every platinum ring, was once forged in a cataclysm like this, a violent collision of dead stars that occurred billions of years before our solar system even formed. But the revelations did not stop there. By combining the gravitational wave signal, which told us the distance to the event, with the redshift of the host galaxy, which told us how fast it was moving away, astronomers had a powerful new way to measure the expansion of the universe itself. This single event marked the true dawn of multi-messenger astronomy, the ability to observe the cosmos using more than one sense at a time. We are no longer just looking at the sky or just listening to it. We are now doing both simultaneously, turning a silent movie into a full sensory experience and uncovering the violent, creative forge where the heaviest atoms of our world are born. That cosmic forge of gold and gravity waves revealed a universe teeming with physical phenomena. Yet the ultimate question remains unanswered. Are we truly alone? On a warm Ohio evening in August 1977, a volunteer for the SETI project named Jerry Amon was reviewing computer printouts from the Big Ear radio telescope. The data was typically a sea of unremarkable numbers and letters, a record of cosmic static. But then his eye caught something that made him grab a red pen and scrawl a single, emphatic word in the margin. Wow, the signal, which lasted for a full 72 seconds, was a stunningly powerful, narrowband burst of radio waves. It was exactly what scientists had predicted a deliberate, intelligent transmission from the stars would look like. It came from the direction of the constellation Sagittarius. It occupied one specific frequency, and it was over 30 times stronger than the background noise. The Big Ear telescope was fixed to the Earth, so as our planet rotated, the signal would naturally rise and fall in intensity as it passed through the telescope's twin beams. The printout recorded this perfect curve, a signature that confirmed the signal came from a fixed point in the celestial sphere. The excitement was short-lived. Despite repeated and exhaustive searches, the signal never returned. It was a cosmic one-hit wonder, a single, brilliant shout that has echoed in silence ever since. For decades, astronomers have tried to explain it away. Could it have been a secret military transmission, a reflection off a piece of space debris, or a passing comet? Each natural explanation has been systematically dismantled. Comets were not in that part of the sky, human satellites did not match the profile, and the frequency was one that is internationally protected, reserved for listening to the cosmos, not for broadcasting from Earth. The WOW signal endures precisely because it fits the profile of an artificial beacon so perfectly, while every attempt to find a natural cause has failed. It stands as a tantalizing, solitary data point, a ghost in the machine of cosmic search. It taught SETI scientists a crucial, humbling lesson. The universe is vast, and our window of observation is incredibly small. We might have been listening to the right place at the exact right moment, but for only 72 seconds out of the last 45 years. This single event, a fleeting red mark on a faded printout, continues to fuel our deepest curiosity. It is a stark reminder that while the cosmos may be filled with the building blocks of life, finding a definitive sign of another civilization is like searching for a single, specific voice in a hurricane. While we search the cosmos for a single sign of intelligence, a new eye has opened in the void, showing us a universe far stranger and more mature than we ever dreamed. The James Webb Space Telescope, orbiting 1,000,000 miles from Earth, has begun its work, and its first images are not just beautiful, they are revolutionary. One of its most startling early discoveries involves the very first galaxies. Our models suggested the early universe should be a time of chaos, filled with small, clumpy, and irregular infant galaxies slowly building themselves up. But when Webb peered back to a time just a few 100 million years after the Big Bang, it saw something that defied those expectations. It found galaxies that were not only massive but also incredibly structured, with well-formed disks and spiral arms. These cosmic toddlers, seen at the dawn of time, look as mature as galaxies that have had billions of more years to evolve. It is like finding a perfectly articulated sentence in the first paragraph of a novel that has just begun. This forces a profound question. How did these colossal, ordered structures assemble themselves so quickly? Our entire timeline for galaxy formation is being challenged, suggesting that the early universe worked in overdrive, creating order out of the primordial fire with a speed and efficiency we do not yet understand. Beyond these galactic giants, Webb has turned its golden eye toward distant exoplanets, transforming them from faint dots into worlds with known atmospheres. By watching the minute dimming of a star's light as a planet passes in front of it, Webb can dissect the starlight filtering through that world's air. It reads the chemical fingerprints left by molecules in the atmosphere. In one of its earliest breakthroughs, it detected carbon dioxide in the atmosphere of a gas giant over 700 light-years away. This was more than a technical first. It was a proof of concept that we can now routinely begin to inventory the air on alien worlds. The telescope has since found water vapor, methane, and even potential hints of other molecules in the skies of these distant planets. While these are not signs of life, they are the essential tools we will one day use to find them. We are no longer just counting exoplanets, we are beginning to take their atmospheric pulse, moving from a cosmic census to a true comparative study of worlds. And closer to home, within our own galaxy, Webb has provided stunningly crisp new views of star formation. Its infrared vision pierces through the thick, obscuring dust of stellar nurseries like the pillars of creation, revealing the process in exquisite, almost violent detail. We can see hundreds of previously hidden newborn stars, their powerful jets blasting away cocoons of gas, and the intricate structures sculpted by their fierce radiation. These images are more than just portraits. They are dynamic snapshots of the very process that forges the elements and builds planetary systems. Each new dataset from Webb is not simply adding to our knowledge, it is actively refining, and sometimes appending, our models of cosmic evolution. We are witnessing a telescope that is not just answering old questions, but revealing a universe so rich and complex that it is generating entirely new ones, forcing us to rewrite the story of everything. From the faint hiss of the Big Bang to the brilliant flashes of colliding neutron stars, these 25 discoveries have peeled back the layers of cosmic reality one by one. We began with a static, small universe, and have ended with a cosmos that is vast, dynamic, and profoundly strange. Dark matter weaves an invisible web that holds galaxies together, while dark energy pushes the entire cosmic fabric apart at an ever-increasing rate. We have felt the ripples in space-time from black holes and watched the very elements of our bodies forged in stellar explosions. The sheer number of worlds out there staggers the imagination, and the possibility of life feels less like a fantasy and more like a statistical certainty. Each discovery did not just add a new fact, it fundamentally rewrote the story, revealing a universe that is grander, more mysterious, and more beautiful than we ever dared to conceive. And the most thrilling part is that this story is far from over. Every answered question births a dozen new ones. Every new telescope, every new detection, peels back another layer, showing us that the cosmos is an endless puzzle. So tell us, which of these cosmic revelations shifted your perspective the most? Let us know in the comments, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our next adventure into the great unknown is just beginning.